So, we have done MPI functions, right. I mean, I gave simple examples and illustrated how these functions will work. Real computation programs will involve more complex tasks, and your projects will be involving some of those tasks. Okay. But you do not need anything more than what I told you, the send, receive, gather, broadcast and reduce. Reduce you need quite often. Okay. So, let us see illustrate that those examples for NumPy array. Those were this earlier ones also are NumPy arrays, but I will do slightly more complex example, slightly more, nothing really complex. So, NumPy arrays and MPI 4pi, okay, and you need it for your project. So, finite difference scheme, I covered this scheme, basics of it. So, we will do it for only two processors. Okay. So, if you have two processors and my data is, so you look at the top part. Okay. So, I have my data is in 4 by 8 array, 4 rows, row 1, row 2, row 3, row 4 and 8 columns. And well, my numbers are, you can see in the top, just focus on the top. Okay. So, but I divide those numbers into two processors, clear. So, processor P0 and processor P1, and the data is divided cleanly. With you need more processors, then you will have, if a big data then only you should divide, if you have small data do not divide, but this for illustration. So, you have 16 plus 16 32 data points and I am dividing it like that. Now, if I am doing finite difference scheme, if I take a derivative here to central difference, which requires left neighbor and right neighbor or top and bottom. Okay. So, in 2D for x derivative I will need, if I compute derivative at this location, then I need values in the left and right, as well as for x derivative I need left and right, for y derivative I need top and bottom, clear. So, we do it as u x plus, my formula derivative d u by dx is u x plus delta x minus u x minus delta x by 2 delta x. I am keeping y silent, and for y you do similarly. Okay. So, the derivative at this location can be performed by processor 0, no problem. But if I want to compute derivative here, then there is a problem, x derivative. I need a value in the left and in the right, but right is not available in this processor. So, right value is available here in processor P1. Okay. So, I need to get that column, actually I need only single column of P1, which okay, and need to transfer it. So, that is what is written here. This arrow shows that I need the first column of P1, this column, all of it should go to the left. So, instead of 4 columns I need 5, I keep 5 columns. One is a column which is from the coming from P1. Okay. For y derivative there is no problem, I have the values at the top and bottom for at any point. Okay. I am not worrying about the edges. For periodic boundary condition we need to copy it at the top and bottom, but let us not worry about edges. Okay. You need to implement it as in sequential code. Of course, if it is periodic boundary condition, then one thing is you should remember that I need to compute derivative here, then I need to go to the left and left is here. So, it is in a circle, but let us ignore that part. Now, for the processor P1, if I want to compute derivative here, no problem, I have left and right, top and bottom, but if I want to compute derivative here, then I have a problem. I do not have, I have the right element in the right, but not in the element in the left. So, I need these data to be transferred to P1. So, this is also we need an extra column. So, that will also be 5 columns 4 rows, all right. So, I have the color convention here is the processor P1 is all gray and processor P0 is light gray, okay, is basically brownish light gray. Okay. So, I need to transfer this data, well you got it, okay. One column from P1 to P0 and one column from P0 to P1. Assuming no periodic boundary condition. If periodic boundary condition, then there has to be done something for the left as well, and the idea will extend to more processors, right, no problem. So, if you have 4 processors and at the edge we need to worry about at the edge. Okay. After send receive, what happens? So, we need to do the send receive, but send receive not of a single number, but full column. We send the full column, which can be done. MPI will manage it. In fact, you can, it is better to send big data chunk, not small data chunks. So, after this operation, send receive operation, this column has come here. So, you can see 0, 8, 16, 24, and this column here has come here 3, 7, 11, 15, 3, 7, 11, 15. Okay. So, that is what we need to do. So, let us write a code. Okay. Please keep in mind that these data are 0 to 15 and these are 0 to 30. So, I just multiply by 2, okay, just to contrast. The P1 has double, every number is double of what is in P1, corresponding P1, P0. Okay. So, code is reasonably easy, I mean this is the code. So, we have I create, as I said, 4 rows and 5 columns, nx is row and ny is column, and start with 0. Please keep in mind that this code is running on both the processors. Okay. There is no global program, there is a single program which is running on all the processors. So, in parallel programming, that is a trick. In MPI, same program runs for multi-processing, multi-threading. Some functions are running on different things. So, this is what you need to keep in mind. Okay, this is what you need to learn. So, I create for in each processor, this will be created 4 by 5 arrays, and I need to assign this arrays with 0 to 15 in P0 and 0 to 30 in P1. So, this is what you need to be doing carefully. So, rank 0. So, this line is nice. I mean, this Python has such a powerful basically powerful ways to do. In one line you can do a lot of many things in one line. Okay. So, I want to create 0 to 15. No? So, I just create make a range function, and this will create a nx into ny minus 1. What is ny minus 1? For this example is 4, right, 5 minus 1, 4. 4 into 4 is 16. So, this is going to create a 1D array of 0 to 15, but I do not want 1D array, I want a 2D array. This is 2D array, right, this is 2 by 4 by 4. First I create 4 by 4, I am not creating 4 by 5. So, I do this function called reshape. So, this same data can be reshaped. So, 1D data I want to shape into 2D data. So, it is nx times ny minus 1, which is 4 by 4. So, it takes this data which is long chain and makes a 2D matrix. Okay. So, this is the beauty of Python, and the type I specify, it is float 64. It is good idea to define type. With MPI you are sending data and it needs to know what is the data size. So, it is recommended that you define the type. So, when I send it, I will have MPI double. For rank 1, so this rank, okay, now this is rank 0 is no problem, 0 to 15 done. Rank 2, well, it is a 0 to 4, huh? So, for rank 0 it is 0 to 4, rank, I think I am making a mistake. Rank 0 it is 0 to 4, that is columns 0 to 3. Rank 1, I have to save it in column 1 to 4, not column 0. With column 0 I am reserving it for data coming from P0. So, these are all rows, colon means all rows, but column 1 to 5, 1 to 4 in, okay. 0 is kept empty right now. So, same idea, just create a 1D array of 0 to 15, then multiply by 2. So, it's one line. So, that makes it 1D array of 0 to 30 of type float 64. So, this is 1D array creation, and then I reshape it to 2D array into 4 by 4. So, this will make a 2D matrix whose contents are 0 to 30. Clear? Now, I need to make a receive buffer. So, where the I am going to send. Okay. So, as we discussed, this column will go to the right and this column will come to the left. So, where should I receive it? So, create a receive buffer which is empty, but whose size is number of rows n x. Also, it is not a good idea to put 4 by 4 in this thing. Okay. Keep as general as possible. Right now, my matrix is general, but my number of processes are only 2. In fact, we should write codes where number of processes are also general. Right? You do not want to say that my code will only work for 2 processes or 4 processes or 1000 processes. It should run for any number of processes, but this for illustration. So, okay, I am doing it only for 2. So, by the way, if I want to do it for n processors, then I have to put a loop here. If rank equal to p, then I need to divide accordingly. So, you can do it in a loop. Now, I start sending the data after creating this receive buffer. So, if rank equal to 0, then I create a 1D array which is a column. Okay, which column? ny minus 2, which is 5 minus 2 is 3. So, this column is what I pick, and I create a object called u0 to 1, this variable is an array. In fact, it is created like the NP array. I take these values and I create NP array, and then send it. So, you need to specify which data to send, which is u0 to 1, and destination, and I put a tag, but it is not really required. I put a tag here. Okay. So, tag 11. So, this is to be sent by the rank 1, which is this rank 1, this guy also has to send a data. So, this data is being sent. So, where is it? U colon comma 1. So, it is the first column, first Python column. Okay. The column starts from 0, 1, 2, 3, 4. So, this is in fact, in our I will say is column 2, but Python will say is column 1. Okay, because column 0 is the first column. So, this column Python column 1 is stores in 1 to 0. Okay, and then it will want to send it 1 to 0, and it sends to disk 0. But as we said, for deadlock we should avoid sending simultaneously, right. So, what should the processor 1 do first? First receive it. So, rank 0, which is master node, sent it. Now, processor 1 should not say I will also send it. Processor 1 should say let me first receive it. So, it receives this data. Which data is receiving? This data, and I use the tag, but since it is receiving only one packet, the tag was not necessary. Okay, but it is okay to use tag. In fact, if to a reader it has one, this is the packet which processor 1 is receiving. So, receiving it, and where is it kept? In receive buffer. A receive buffer is copied into u colon comma 0, which is here. So, all rows, but 0 column. So, u colon comma 0 is receive buffer. Okay. And I am printing it for verification. That is what being done. After receiving it, processor P1 will send it, and this data is sent. Which one? This data is being sent, and then P1 is P0, sorry, master node is receiving it, receive here, and is where is it copied? Last column of P0, which is ny minus 1, which is 4, Python 4. So, Python 4 is here, this is where I copy it. Okay, great. So, this is how we send and receive columns, and all the people who are doing finite difference project should implement this for general number of processors. I did it for 2 for illustration, and you can do it for P. Just keep in mind that the same code we is running on all the processors. Okay, that is what you need to keep in mind. So, you have to make sure, okay, if I am process 0, what 1, what should I do, and this should be coded in the program.